Welcome to my chemical process calculations classroom. So in this model number 2, we have been discussing about numericals on material balance in unit operations, that is without chemical reactions. In that we have been discussing about dryers. In the previous lecture we have seen how to solve numericals involving material balance in dryers. In that we have seen 3 cases, and now we are moving further to solve numericals, in which we are going to consider what is the flow rate of air, what is the moisture present in it. Okay, so in a dryer, mostly in dryers, air is the medium which is used to remove the moisture from the substance, solid substance. Mostly it is solid substance. There are cases where it can be liquid or gases also. So what happens is we take the atmospheric air and we preheat it, and the hot air enters the system where it will absorb which will collect some of the moisture present in the solids, and it will leave with more moisture. So the inlet air will have less moisture, that is less water vapor present in it, and the outlet air will contain more air present in it. Okay, so that always it is going to gain moisture, gain water vapor. So the air leaving the stream will be more uh, water vapor content. The water vapor content in the air leaving the system will have more moisture content. Okay, so that's what happens in a drying operation. So this drying operation is important, as I told you. In most of the pharmaceutical industries, whatever composition of the medicines that is made, tablets are made, the excess moisture has to be removed. So the excess moisture will be removed by using drying operation. In cement industries, whatever the cement is made, the excess moisture has to be removed in rotary kiln, and various industries, most of the industries, this drying operation is carried out. Okay, so we should able to calculate what is the rate of which the air is being circulated, because remember we have to heat the air. So to perform energy balance, we should know what is the rate at which this air is being circulated. We will do some numerical on this topic. Okay, in air water system, that is where we have atmospheric air in which we have water vapor. For such system, actually this system we come across in cooling towers, in air conditioners, all these places we have this air water system, where we will be making use of psychometric chart, where psychometry refers to the science of measuring water vapor content present in the air. Okay, so actually we will use some thermometers to measure the what is wet bulb temperature, what is dry bulb temperature, and using the psychometric chart how you can relate it to find out the humidity. Okay, so all that you will learn in another course. So right now here we are going to make use of definition of humidity in these drying operations. So as and when required, we will define each different humidity terms. Currently we will use humidity. What is humidity? It is the measure of water content present in the air. It is the measure of water content present in air. Okay, so if mathematically, it is the ratio of mass of water vapor per mass of dry air. Mass of water vapor per mass of dry air. So it can be in terms of mass, or you can even express in terms of absolute humidity in terms of moles. You can multiply by the respective molecular weight. For example, water it is 18, for air it is 28.84 kg per kg mole. So you can put them in ratio in that way also. Okay, so you can define absolute humidity as the mass of water present in per mass of dry air. Okay, so that is the definition of absolute humidity. We know the definition of absolute humidity now. It is the ratio of kg of water vapor per kg of dry air. Okay, denominator is dry air, it is absolute humidity. Okay, so take down this problem. Milk powder is produced in a spray dryer. Milk powder is produced in a spray dryer which evaporates all of water in it. Milk powder is produced in a spray dryer which evaporates all of water in it. The operation is shown in the figure, associated figure. Operation is shown in the figure. Assuming that inlet air contains no water, calculate the production rate of milk powder and molar flow rate of inlet air. Assuming that inlet air contains no water, calculate the production rate of milk powder and molar flow rate of inlet air. Okay, So the figure is given here. So what is there? There is an inlet stream of milk with a 70% of water. It is weight percentage. Okay, because there is, whenever it is mole percent, it is specifically mentioned. You can see that in the wet air that is leaving the stream, it is given 12 mole percentage water. So that means here it is not mentioned mole percent, so therefore it is weight percentage. So inlet milk is having 70% by weight water, and finally dried milk powder is leaving. Totally it is dried milk, there is no moisture present in it. Okay, and we have a inlet air, which is free from moisture. That is the assumption it is mentioned. So we have inlet air which is free from moisture, and we have wet air leaving the stream, and the conditions are given here. So what are the conditions given here? So conditions given are, it is given that 12 mole percent moisture is present, and the volumetric flow rate is 18,000 meter cube. 18,000 meter cube of is the volume of wet air that is leaving the system, and temperature and pressure are given 358 Kelvin and 101.325 kilopascal. So first let us write the given data. Okay, let us solve the problem. Please take down the problem, and you can draw the sketch on the notebook, so that it will be easier for us to proceed with the calculations. Okay. So here we are trying to solve this numerical where flow rate is given in volume. So first let us write the given data. So data given are, so here it is given that pressure is equal to, let me choose the pen. So what we can write is, it is given that pressure is equal to 101.325 kilopascal. So pressure, temperature is given, please write down that 358 Kelvin, and volume is given 18,000 meter cube, and mole percentage of water is given, which we will make use of later. So this volume we can convert to molar flow rate of air leaving the system, wet air. Okay, so we can write molar flow rate of wet air. Wet air means here the air leaving the system, dry air. Okay, so the molar flow rate is, what is ideal gas law? If we assume PV equal to nRT, so N equal to PV by RT. We have done several numericals in the previous lecture, you can refer to the videos. So here P is 101.325 kilopascal into volume is 18,000 meter cube, and we have R value, so we know R value is 8.314 kilopascal meter cube per kilomole Kelvin. Okay, so that value you can substitute 8.314 kilopascal meter cube per kilomole Kelvin into temperature is 358 Kelvin. So what is N value? So that is the molar flow rate of leaving air is, please use your calculator, 101.325 into 18,000. So please use the value. So what you get is 612.75. 612.75. Take your own time to calculate the value. 612.75 kg moles per hour. So if it is given, let us assume it is given like kg mole, 18,000 meter cube per hour. So this is 612.75 kg moles per hour, and it is given that the leaving stream contains 12 mole percent water. The leaving stream contains 12 mole percent water. So this is the total amount of air that is leaving, wet air, total amount of wet air that is leaving is 612.75 kg moles per hour. Okay, so actually is it the value in kg moles per hour? Okay, so now it is mole percentage only given, no, so there is no issue now. So it is given 12 mole percent is water. Out of this much 612 kg moles, we have 12 mole percent water. Therefore amount of water, you can say that amount in kg moles of water in wet air, amount of water in the wet air is equal to 12 mole percent of N. Okay, so that is 0.12 into 612.75 kg moles per hour. Okay, so this is equal to, this is a calculator, 0.12 into 612.75, 0.12 into 612.75, which is equal to 73.53. Are you getting the same? Please write your answer, one answer. .53 kg moles per hour is the amount of water present in wet air. Okay, so we can convert these to what is the kg of water present in the wet air. What is the amount of water? You can say amount in kg, that is mass of water. Okay, so amount of water in wet air is equal to, we have 73.53 kg mole multiplying by molecular weight. Molecular weight is of water 18 kg per kg mole. So kg mole gets cancelled. So what we get is this much kg. Please calculate how much kg you get. So how much kg we get with your calculator? So 73.53 multiplied by 18 is equal to 1323.54. 1323.54 kg. So are you getting the same value? So this is the amount of water that is present in air, wet air. Okay, so let me save this file. Okay, so now we can further proceed this. So let me clear this screen. Now what you can do is, you can, now we have calculated the amount of water that is present in the leaving air, right? So that is 1323.4 kg. Let me write it here. Okay, 1323.4 kg per hour is the amount of water. Okay, amount of water in leaving air, that is wet air. Okay, now what is the amount of molar flow rate of dry air leaving the dry air? Okay, so we have amount of water in leaving air is 1323.4 kg per hour, and we have just calculated what is our we have 73.53 kg mole is the amount of water. Okay, what is the total kg moles we have calculated? Sorry, total kg moles is equal to N equal to 612.75 kg moles. Okay, so from this we can determine molar flow rate of dry air leaving the dryer. Okay, that's what I was telling you. Molar flow rate of dry air leaving the equipment or dryer. So what is the molar flow rate of dry air leaving the system? So that is total 18,000 meter cube of volume is leaving. From that PV equal to nRT, we calculated the N value of 612.75 kgmoles per hour, and we calculated what is the amount of water associated with it, that is 73.53, which is 12% of it. Okay, so we can find out this value, the difference, that is 612.75 minus 73.53 gives us the value of kgmoles of air of dry air that is leaving the system. How much kgmoles per hour? You please calculate using the calculator. So what we get, subtracting 539.2. So if you subtract it, you get 539.2 kgmoles per hour of air that is leaving. So remember, in a dry air, whatever is the amount of, we have a air entering, we have wet air leaving. Okay, so this air contains dry air plus moisture. Wet air also contains dry air plus moisture. Okay, there are some cases where it will be saying that the amount of moisture is 0. Okay, so that in this case also that is the case. It is assumed that air entering is not having moisture. So what the point I am trying to convey here is, if you look at the individual material balance for dry air, individual material balance for dry air in air that is circulated, so whatever is amount of dry air entering the system, that will be the same amount will be leaving the system. So what we have calculated is this much kgmoles of dry air is leaving the system, that is 539.2 kgmoles per hour is leaving the system. Okay, so if you look at the individual material balance, we have so what you can write is amount of air entering is amount of dry air. Amount of dry air entering is equal to amount of dry air leaving. Okay, so that is based on the given assumption, inlet air has no water, so we have calculated this molar flow rate of dry air leaving the dryer. I have saved this file. So now what we can calculate is individual material balance for water. So individual material balance for moisture. So what is the individual material? Let M be the milk that enters the dryer. Let M be the milk that is entering the system. So what it is given? It is containing 70% water. So it is given milk contains 70% water. So what is the amount of water in milk entering? Equal to 0.70 into M. Okay, and remember during drying all the moisture is removed, and we have calculated the amount of water removed, amount of water in with here. We have calculated it to be 1323.4 kg per hour. Okay, so this much amount of water is leaving means that should be equal to, because from the during in the drying operation what we get is milk powder which is free of moisture, that is 100% removal of moisture. Okay, so whatever is the moisture that is present in the feed is this much then. So that way amount of moisture is equal to this much. So okay, so we can find out m value now easily. So 0.7 times m is equal to 1323.4. That is the balance for water individual balance. Okay, so individual material balance water. So the milk that is entering will have 70% of water, and that all the amount of water is carried away by the air. Remember, air is entering without any water, therefore whatever is the amount that is only taken from the milk. So by making that individual material balance, what we get is m value. So m value equal to 1323.4 divided by 0.7. This is your calculator. 1323.4 divided by 0.7 equal to, so what we get is 1890.5. okay, so what we get is 1890.5 kg per hour. So you can round off the value whatever you get. Okay, so this is the amount of milk that is entering the dryer. Okay, so now what you can do is, now we have found out what is the total milk. Okay, so m value we have determined. So we have determined m value to be 1890.5 kg per hour. Okay, so remember what is milk? Milk contains whatever is the milk entering, that should be equal to milk powder produced plus water evaporated, right? So F equal to product plus water evaporated is our general material balance, overall material balance. Okay, so what we have is, here we have considered F to be m. Okay, so that way we have 1890.77 or 0.5, 1890.5. okay, I got around 0.57, I will make it 6. okay, 1890.6 is equal to whatever is the milk powder produced plus water evaporated. So water evaporated is, how much water is evaporated here? 1323.4. okay, so then rearranging we get milk powder production rate is equal to 1890.6 minus 1323.4. how much? Please do the calculation. So we get around 566 kg per hour of research. That is the question, right? So question, if you refer to the question, so it is asked that calculate the production rate of milk powder and molar flow rate of inlet air. Okay, so first step we have calculated. Now what is the milk powder production rate? Okay, Okay, so what is the answer for the second part? As I said in the question, it is asked what is the calculate the production rate of milk powder, which we have determined it to be 566.2 kg per hour. Another question, what is the molar flow rate of inlet air? What is the molar flow rate of inlet air? We have calculated the amount of dry air entering is equal to amount of dry air present in the leaving stream, right? So that way, that is the assumption, right? Inlet air is free from moisture, so whatever is the amount of dry air leaving, that is the molar flow rate of air that is entering the system. So what we can add? So we can add the answer as answer for the second part is the amount of air entering is equal to amount of air leaving. So that is the answer for B part of the question. A part of the question, so we have determined what is the production rate of this. So answer for B part is, answer for A part is 566.2 kg per hour of milk powder is produced, and here the amount of air that is leaving, dry air leaving is 539.2. Therefore molar flow rate of, right from the question, so refer to the question here. So what is the question? Molar flow rate of inlet air. So molar flow rate of inlet air is equal to 539.2 kg moles per hour. Remember here water moisture content in the air entering is 0, that's why we directly write it. Okay, so otherwise if there is some initial moisture present, so we have to take care of that also. Okay, so these are the answer for this particular question. Okay, yeah, let us do another problem. Here we are going to consider the air that is being recycled. So when usually the air is hot air, right? So we don't want to just send the air, heat the air and allow it inside and send it out without reusing it. Okay, so to recover the heat, it is always preferred to recycle some amount of air because it is already at certain temperature. Okay, but we have to add some fresh stream of air also. Okay, because we have to maintain the moisture content. Okay, so means we have to remove the moisture content from the solids. So usually certain amount of air will be recirculated into the system and a certain amount of fresh air will be leaving. So at steady state, so you have certain amount of air being recirculated within the system. Means it will be mixed actually. For the air that is leaving the stream, a portion of it will be withdrawn as exit and certain amount of air will be recycled to the thing. How recycled means a certain portion is taken out, returned back, and it is mixed with the fresh feed. So a mix of recycled air plus fresh air will enter the drying unit. So, okay, so that's what happens in such systems. So here we have a slab problem, please take note. Slabs of building board containing 16% moisture by weight are dried to a moisture content of 0.5 percentage. Slabs of building board containing 16% moisture by weight are dried to a moisture content of 0.5 percentage. Okay, so initial moisture content in the solids is 16%, in the final solids it is 0.5 percentage. Okay, so it is clearly mentioned it is recirculation of hot air is taking place in the system. Okay, recirculation of hot air is taking place. So continue with the question. The fresh air contains 0.02 per humidity. 0.02 humidity. So humidity can be represented as 0.02 H. If it is simply given 0.02 capital H, it means the fresh air contains 0.02 humidity. What is humidity? We have seen the definition. Okay, it is the kg of water vapor per kg of dry air. Okay, the exhaust air contains 0.09 humidity. So it is mentioned that the exhaust air contains 0.09 humidity, the fresh air contains 0.02 humidity. Okay, calculate the quantity of fresh air required per 1000 kg per hour of dried board if the fresh air is supplied at a temperature and pressure of 301 Kelvin and 101.325 kilopascal respectively. Okay, so yes, I repeat, slabs of building board containing 16% moisture by weight are dried to a moisture content of 0.5% by weight by recirculating hot air. The fresh air contains 0.02 humidity and the exhaust air contains 0.09 humidity. Calculate the quantity of fresh air required per 1000 kg per hour of dried board if the fresh air is supplied at a temperature and pressure of 301 Kelvin and 101.325 kilopascal. Okay, so this is the question. Try to solve this. First, draw a block diagram. So we have to solve this problem now. So first let us write the given data. So first draw a diagram to understand what is given in the numerical. Okay. So first what we are going to do is we will draw a diagram. First I should choose the pen. So what we have is we have a system, so which is a dryer. Okay. So we have wet solids entering, that is our feed is wet solid, that is our building material, right? So building material is entering and it is given that it contains 16% moisture. So the feed contains 16% moisture, it is given. Okay, 16% moisture is present in the feed that is entering. Okay, so this leaves the product. So we have our dried product, dry solids. So here it is slab. Okay, material here is building material. Okay, building material. So here material, solid substance is building material, building blocks. Okay, so slabs of building block, that is the material. Slab of building blocks is the material. I am just writing wet solid. So this material, when I say wet solid, it refers to material is the slab of building blocks. Okay, so and it is mentioned that dry solids contain 0.5% moisture. Okay, so inlet feed contains 16.5% moisture, 16% moisture, and the product contains 0.5% moisture. So that's what happens to our inlet of the feed and product. So the moisture, it leaves out some vapor, right? Water is to be removed, moisture is removed. What happens to the moisture? That's what now we are going to do here. Okay, so we have a fresh air entering the system. Okay, a fresh air is entering, and so whatever is the product leaving, so out of which we are going to have fresh air leaving the stream, and you have exit air. Okay, that is wet air, right? In the previous problem we wrote it as wet air. Okay, so here it is fresh air is coming. Okay, so what happens is, so out of this product air that is leaving, certain portion of the air is returned back, that is recycled, right? Certain portion of air is recycled, so that air is recycled air. So a certain portion, whatever is the amount, let me say it is 100 kg. So this 100 kg per hour is keep on getting into the system, but whatever is the fresh air amount, and we are going to have wet air that is leaving the system. It can be exhaust air also. Okay, exhaust air, fresh air. Okay, we have fresh air, we have exhaust air, and we have recycled air. Okay, so now what is the basis for this problem? Basis is we have basis is given 1000 kg of dried product. Okay, so 1000 kg of dried product. So here you have dry solids and we have this thing. So we have that solid will contain 99.5% dry solids, 99.5 percentage dry solids. So that, let me say, product or product stream contains 99.5% dry solids and 0.5 percentage water. Okay, so here it is given that this one is given. What is that? 1000 kg per hour of dried product. So our dried product is 1000 kg. And what is the amount of dry solid, what is the amount of moisture can be determined, right? So we can write the amount of dry solids in the product is, that is in the dried product, is equal to 0.995 into 1000, which is 995 kg. Okay, so if this is 1000 kg per hour, this also kg per hour. So similarly, amount of moisture in the product, amount of moisture present in the product is equal to 0.005, or you can say that total dried products minus dry solids present in it, which is 995 kg. So what you get is this much kg per hour of moisture is present in the product. That value is just 5 kg per hour. Okay, so this is the amount of water that is present in the product. Okay, remember now we know the amount of dry solid present in the product. So what will be the amount of dry solid present in the feed? Okay, so that can be determined, right? So what you can write is same amount of dry solid is present in the feed stream. Okay, so what is the feed stream? Let F kg per hour is the feed stream. Okay, so it is given that feed contains 16% water, which means 84% dry solids. Okay, so what is the individual material balance for dry solid? Individual material balance for dry solids is whatever is the amount that is present. Let xf is the mole fraction, xf into f is equal to xd into d. So this amount we have already calculated as 995. Okay, so xf is 0.84, f is unknown, so we will get f value now. xf into f is equal to, this is the individual material balance for dry solids. Let xf be the mass fraction of dry solids present in the feed stream, that is 84%. Let f be the kg per hour of feed that is entering the system, which will be equal to, because the same amount of dry solid will be present in the product, which we have determined already. It is given that 0.5% of water, so therefore it is 99.5% is dry solid, therefore 0.95 xd, this is xd value. Okay, we have xd equal to 0.995 and d equal to 1000, so we got this value 995. So f value also we get, so 995 divided by 0.84. Please use your calculator. How much? Switch on the calculator, please. 995 divided by 0.84 is equal to, in engineering mode, 1184.5. 1184.5 kg per hour is the feed flow rate. Okay, this is the rate at which the feed is entering. So if f is known, we should know how much is the moisture present in the feed, right? So we can write moisture present in the feed is equal to moisture present in the feed is equal to 16 percentage, right? 16 percentage of F, that is 0.16 of 1184.5 kg per hour. So that is much kg per hour. This is your calculator. So already we have the answer into 0.16 equal to, we get 189.5. 189.5 as the answer. We get 189.5 kg per hour is the mass of moisture present in the feed. Okay, if this is the thing, so we can find out the molar flow rate of thing. So what is the amount of water removed now? This is the moisture present in the feed, and 5 kg is the amount of 5 kg is the moisture present in the product. Okay, so in the feed we have 189.5, in the product we have 5 kg. So what is the amount of moisture removed? Amount of moisture removed is equal to 189.5 minus 5. So what is that? This is the amount of moisture present in the feed minus amount of moisture present in the product. So what we get is 184.5 kg per hour is the moisture removed. Okay, remember now what we have to do? So the moisture removed is equal to moisture gained by the air. Okay, so what you can write, another material balance for moisture, individual material balance for moisture is moisture removed from feed is equal to moisture gained by air. So we are going to make use of this concept, that moisture, whatever is the moisture removed by the air, moisture removed from the feed, these wet solids, in this case building materials, slab building blocks. So that moisture is gained by the air. Okay, so now we can solve this problem. Okay, so how to go proceed further? Let us say let A be the flow rate of fresh dry air. Let A be the flow rate of fresh dry air. Then what is the moisture gained? Remember, a fresh air is entering. Okay, it has a initial moisture, humidity is given. It has absolute humidity, and we have a system. Forget about the what is happening inside. Overall, what is happening? So we have exhaust air, which has a humidity H2, H1. Both are given, right? So what is humidity? It is the kg of water vapor per kg of dry air. Okay, so this fresh air is what we are defining now. The fresh air contains dry air. Fresh air contains dry air plus moisture. This fresh air contains dry air plus moisture. Please understand it clearly. I repeat, H is the absolute humidity, where humidity is kg of water per kg of dry air is given. So the value for this problem is also given. Feed air is dry air actually, right? So it is 0.02. Exhaust air contains 0.09 kg of water per kg of dry air. Okay, so whatever is the fresh air, so that fresh air contains some amount of dry air and some amount of moisture. Okay, so I am defining, let this amount be A. Let this amount be A. What is the associated moisture? Now we can write out that, right? So what we can write is moisture gained is equal to, we can write moisture gained is equal to A into, see, whatever is the dry air, remember whatever is the amount of A is the dry air that is entering freshly, means the same amount of dry air will be leaving the system also, right? So the dry air associated with this is going to be the same regardless of what is being recycled here. Okay, so the whatever is, let us say 10 kg per hour of dry air is entering, the exhaust air will contain 10 kg of dry air. Okay, so that is the at steady state condition. At steady state, whatever is the amount of dry air entering, the same amount of dry air will be leaving. So that amount we consider it to be AB, the flow rate of fresh dry air. So then A into moisture gained is equal to A into 0.09 minus 0.02. Okay, so when we multiply by this humidity 1 minus humidity 2, so we get the moisture gained. Okay, so A is the amount of water gained, so this is 0.07 A into 0.07, because A is, what is the unit of A? A is kg dry air. 0.07 is, what is the difference? H unit is kg of water vapor per kg of dry air, right? So this dry air will get cancelled, so we will get kg of water, this one. Okay, and this amount is equal to moisture removed. What is the amount of moisture removed? We have calculated it to be 184.5 kg per hour. Okay, so this is equal to 184.5. so solving this, what we get is A value. Please get A value, please use your calculator. A is equal to 184.5 divided by 0.07, which is equal to 2636.0, we have rounded it, kg per hour. Okay, so I repeat, so moisture removed from the feed is equal to moisture gained by the air. We have determined the moisture removed from the feed, which is 184.5 kg. So we are having a fresh air entering and exhaust air leaving. So at steady state, whatever is the amount of air being recycled, that is same, but whatever is the fresh air, whatever is the amount of dry air that is entering the system, same amount will be present in the exhaust air also. So what is the moisture gained by it? Because the associated humidity is given. The leaving air is gaining the moisture from the solids, and it is leaving with high humidity. Okay, let me say 0.09 kg of water per kg of dry air. If A is the amount of dry air, then A multiplied by 0.09 is the amount of water present in the system. Okay, so amount of water present in the exhaust air is equal to A multiplied by 0.09. Similarly, whatever is the moisture present in this one, here also the same A is there. A multiplied by 0.02 is the amount of moisture present in the feed stream. So this minus this gives us the moisture gained from the solids. Okay, so A into 0.09 minus A into 0.02 gives us the moisture gained. So which is 0.07 into A is equal to moisture gained. So the moisture gained is nothing but the moisture removed from the feed, which is 184.5 kg per hour. So equating this, we get the value of A, which is 2636 kg per hour. Okay, so if this is the flow rate of dry air, this is the flow rate of dry air, this is the flow rate of fresh dry air, okay, in the fresh stream. Okay, this is 2636. Now what is the moisture associated with the fresh air? Remember, I told you already, fresh air is combination of A plus associated moisture. Okay, water vapor. Fresh air contains A amount of dry air plus this much amount of water vapor. So what is the moisture? So we can find out what is the moisture associated with it, right? So amount of moisture amount of moisture associated with fresh air is equal to, so this A multiplied by H1, right? What is A value? 2636 kg of dry air per hour multiplied by, what is H1 value, which is humidity value, 0.02 kg of water vapor per kg of dry air. So kg of dry air gets cancelled, so what we get is this much kg of water vapor per hour. Okay, please use your calculator. 2636 into 0.02, which is 2% of this. 1% is 263.6 into 2. So we will, sorry, 1% is 26.36 into 2. How much? Please calculate. 2636 into 0.02 is equal to 52.72. 52.72 is the kg of water present in the feed. Okay. So what is the, then question here is, what is the flow rate of fresh air? What is the flow rate of fresh air is equal to, so A plus water vapor, that is 2636 plus 52.72 is equal to this much kg per hour of fresh air is entering. So this is 0.72862. So around 2700 you will get. Okay, so you have 2688.72, you can say 2690, or you can round to 2700 kg per hour. Okay, so around 2700 kg per hour of fresh air is entering the system. Okay, this is the value. But what is the question? Please go through the question again. Exhaust air contains, calculate the quantity of fresh air required per 100 kg if the fresh air is applied this one. Okay, so we have calculated the quantity of fresh air. Okay, so that's the answer for us. Okay, also we can determine the volumetric flow rate also. So we can convert, because there is a temperature and pressure data is given, so we are supposed to express it in volumetric flow rate. Okay, which should be mentioned actually. Calculate the volumetric flow rate of air, because pressure and temperature is given, means we have to convert it into that unit. So that's what I was wondering, what is missing. Okay, so now we have determined the mass flow rate. Okay, mass flow rate of fresh air. Yes, as I said, I am just rounding it off, or you can keep it the same value, 2700 or 2688.72 kg. Okay, so how to find the volumetric flow rate? How to find out volumetric flow rate from mass flow rate? If you know the density. Okay, otherwise simply we can convert, we know the average molecular weight. Average molecular weight of air is equal to 28.8 kg per kg mole. So this is where we are using the concept which we have learnt in the model 1. Okay, so what is the molar flow rate? Molar flow rate is 2688.72 kg divided by 28.84 kg per kg mole, which we will get kg moles. Okay, so this is kg per hour. So what we will get is kg moles per hour we will get. Please use the calculator. 2688.72 divided by 28.84 is equal to 93.23. 93.23 is the, we get 93.23 kg moles per hour. Okay, so this is a molar flow rate. So we can convert it into volumetric flow rate. PV equal to nRT, assuming ideal, it obeys ideal gas law. So volumetric flow rate is nRT by P. So we get n value, okay, n dot actually. When it is n dot, we what we get is V dot. Okay, that is per unit time. So what you can substitute all the values. So V value is equal to, so what is the value, what you get for n? 93.23 kg moles per hour multiplied by V equal to n. R value is, we know SI units, 8.314 kilopascal meter cube per kg mole Kelvin, right, into temperature. What is the temperature in this given problem? It is 301 Kelvin, and divided by pressure. So atmospheric pressure is given 101.325 kilopascal. So show the unit tally. We get kg mole getting cancelled, kilopascal getting cancelled, Kelvin getting cancelled. So what is left out here? Meter cube per hour is left out. So we get volumetric flow rate in meter cube per hour. Okay, so what is the answer? Please use the calculator. I have 93.22 already in calculator, multiplied by 8.314 into 301 divided by 101.325 is equal to 2302.5. So what we get is 2302.6 meter cube per hour of air is required, fresh air. So this is the answer. Okay, so final answer we can write. The volumetric flow rate of fresh air is at a given temperature and pressure. Okay, so at a given volumetric flow rate of fresh air at given temperature and pressure is 230, we can round it off, okay, meter cube per hour. So usually you can even skip these values. So we are getting around 2300 meter cube per hour of fresh air is entering the system. So that is the answer for the required question. Okay, I repeat. So what we have done, is first we determined. So first I'll repeat whatever we have done so far. So we considered a feed which contains 16% of moisture. Okay, that means remaining 84 is dry solids, and it is given that the product is leaving. The product leaving is 1000 kg. It is given. Okay, and it is given that it contains of moisture only 0.5%, which means dry solids present in it is 99.5%. Okay, so what is the material here? It is a slab of building blocks. Okay, so that is the feed entering and leaving, and whatever is the moisture, excess moisture present in it, that is being taken away. So that first portion is to find out what is the amount of moisture that is removed. Okay, so what we did is we considered the feed F, and we have the D value 1000, XD value 0.995. So we equated it to get the F value to be 1184.5 kg per hour. So then to find the moisture present in the feed, it is given that 16% is the moisture present. So what we have done is 16% of F value determined is 189.5. That is the moisture present in the feed, and we know what is the moisture present in the product, which is only 5 kg. So when we subtract that, we get the amount of moisture removed from the slabs, that is building material. 189.5 minus 5 gives us 184.5 kg per hour. Okay, so then we did the individual material balance for water. If we do within the system, it says that whatever is the amount of moisture removed from the feed, that is the moisture gained by the air. Okay, now we are concentrating on the air part. Let there is a fresh air entering the system and exhaust air leaving. Whatever is the amount of dry air that is entering the system, the same amount of moisture dry air will be leaving the system. Okay, so that way we have, let A be the flow rate of fresh dry air, that is dry air entering the system. Then what is the amount of moisture present in the what will be the amount of moisture present in the entering air entering. So air has humidity of 0.02 kg per kg of water per kg of dry air. So 0.02 multiplied by A value gives us amount of moisture in feed of feed air. Similarly here humidity is given 0.09. So 0.09 multiplied by A gives us the value of what is the moisture present in the exhaust air. So what is the moisture gained? So the amount of moisture present in the exhaust air minus amount of moisture present in the inlet air. Okay, so that way A into 0.09 minus A into 0.02 gives us the amount of water that is gained by this air. So we can simply take the A common out and write A into 0.09 minus 0.02, which is 0.07 into A is the amount of moisture gained, which is equal to the moisture removed from the feed, which is 184.5 kg per hour. Okay, so that way we have A value, we get the A value 2636 kg per hour. So that is the amount of dry air that is entering, fresh dry air. So that fresh air, dry air, if you know, we can find out what is fresh air, because we know what is the amount of moisture associated with it. A into H1 gives us the value 2636 into 0.02 is equal to 52.72. So we get fresh air value 2688. So that is the mass flow rate of fresh air. So using the average molecular weight of air, we have converted to molar flow rate equal to 93.23. So we get V value. So we get volumetric flow rate. By using ideal gas law, we get the answer. Okay, 2302.6. Okay, so that is the answer. Lecture we have solved some numericals for in dryers. Okay, so what we have done extra, so we have considered the what is the flow rate at which air is entering, how much recycled air is there, like that we have done the numerical. So only if you practice this numerical, we will be able to solve some more numericals in the next lecture. So it's as a prerequisite for next lecture, please solve these numericals. Okay, so if you have doubts, we will discuss in the next class, and we will solve some more numericals so that you get practice to it. Okay, thank you for joining my classroom. It's bye from me. Thank you.